Good afternoon, students. Can you hear me? Okay, if yes, it's okay. After 1 minute, we will start our lecture.
Hello, Professor.
Hello.
I'm sorry, Professor. I have the question.
Okay.
Will we have the labs today from?
Yes, of course.
Okay.
Today it is beginning from 40.
Yes. Okay. Thank you.
Not at all. Okay, let's start our today's lecture and continue our lectures. Okay, now let's consider this first example. Let's begin with this example. So here we have interpolators, the 4 points. You can see we need to find here polynomial P3 of x, and we have nodes xi. In this case, I from 0 till 3, x0, x1, x2, and x3, and the corresponding yi's we have. So now let's find polynomial. Now, first method. Let's represent the interpolating polynomial as, in this case, polynomial. Yeah, this is the, what was this kind of polynomials? Lagrange polynomial, yeah? So in this case, we have coefficients, unknown coefficients are A0, A1, A2, and A3. And now, from this polynomial, we can find the system with these nodes, xi. If you put instead of x, corresponding nodes, x, for example, in the first case, we will put x0, and we have corresponding y0, and then x1 instead of x, and we get y1, etc. x2, we get y2, and x3 will get y3. So we have how much? 4 equations, system of 4 equations. And now we need to solve this kind of system. So in this case, we have the values of these nodes, x0, x1, x2, and x3. Let's put instead of x0, x1, x2, and x3, the corresponding values of these nodes. So in the first situation, it will be just -2. Instead of x0, it is -2 from this table, yeah? And then this is -2 squared, and then -2 cubed. Now, for x1, it will be -1. So -1, -1 squared, -1 cubed. These ones are the coefficients of this A0. So we have unknown variables now, A0, A1, A2, and A3. We need to find these coefficients from this system. Is it clear? So now we have as x2, this is just 0, the value of x2. And then we can put instead of x2 zeros, 0, 0 squared, 0 cubed. And the last element here, x3, fourth element, this is, yeah? So this is just 1. So here we have Again, the first coefficient here, just 1, and then 1, 1 squared, and 1 cubed. So this is the matrix, the first matrix, just a matrix. Then this is the matrix of unknown variables, A0, A1, A2, and A3. And then this is the matrix of Y. So here you can see Y0, Y1, Y2, and Y3. So in this case, this is equals to 3, 1, 2, and 0. So now we have this now matrix equation, just similar with AX equals to B. Yes. Now this is a linear system, and we can solve this system. How to solve this kind of systems? We will consider the next part of this course. And here we recall the matrix of Vandermonde. If you remember from the previous lecture, we considered Vandermonde matrix. And the Vandermonde matrix is associated with an ill condition problem here. And the solution of this system is, after solving this kind of systems, we'll get here these values. So A0 is 2, A1 is half, A3 is minus 3 over 2, and A2 is minus 3 over 2, and A3 is minus 1. So they are coefficients of our polynomial P3x. Now, here we will replace, substitute, instead of this A0, A1, A2, and 3, the corresponding values of these unknown coefficients. And we'll get kind of polynomial, interpolating polynomial this is. So we get this answer. Is it clear with the first method? We use it here, Lagrange polynomial. I think there is no difficulties with this first method. It's very easy to see. So here, we build system and find unknown coefficients here. Unknown coefficients. So they're given table of nodes. Okay, now let's consider the second method. So we have again this table, same with the first example. So we have again same nodes and same corresponding y's. And now let's find P3x. So in this case, we build this fundamental Lagrange polynomial with this product. Yes, so we have two methods finding. We can find just with this polynomial or with this fundamental polynomial. You can see here P3 of x, this is y0, L0 of x plus y1, L1, y2, L2, and y3, L3, where Li are the fundamental Lagrange polynomials associated to the xi nodes here. So we have xi nodes, we have yi, so we need to find this Li now. First of all, we'll compute this Li by this formula from the definition of fundamental Lagrange polynomials. Look here, in this case, we need to find this product of x minus xi and product of, in the denominator, xj minus xi, j from 0 till n. Let's find this Li. So here you can see computation of this finding this Li. So in the first case, we'll find L0 corresponding to the x0. So fundamental Lagrange polynomial of x0. So in this case, your x0 will be here. Look here. And you need to subtract x0 minus x1, x0 minus x2, and x0 minus x3, like this in the denominator. And in numerator, you have just x minus xi. So beginning from x minus x1, x minus x2, and x minus x3. So you can see if you replace the corresponding values of xi, notice, so we'll get here x plus 1, because of this is x1, value of x1, this is minus 1. And then x, because of x2 is 0. And however x3 is 1, it will be just x1 minus 1. And in the denominator we obtain, you can see here x0, it is just minus 2, minus 2, minus 1 plus 1, minus 2 minus 0, this is just minus 2, and minus 2 minus 1. If you compute the denominator, we get here 6, yes, minus 6 in this case. So now we have this numerator without changing here, because of here it depends on x. We need to find just here coefficient again. So the first coefficient will be minus 1 over 6. So coefficient of this polynomial, you can see here, it is y0. You have y0, this is just 3, and L0x. So L0x, in this case, this is equals to this one. So we need to multiply it to 3. So the next one, this is L1x, corresponding fundamental Lagrange polynomial to the x1. And we obtain in numerator x minus x0, x2, and x3. There are without x1 now. Here without x0. And when we find according to x1, here without x1 now. But in the denominator, it will be x1 minus x0, x1 minus x2, and x1 minus x3. So after replacing the corresponding values, we'll get here 1 over 2. 1 over 2, x plus 2 times x minus 1. So this is now the second coefficient of this polynomial, L1. And now x2. So corresponding Lagrange fundamental polynomial, L2x. So here in the numerator we obtain the expression without x2 now. It will be just x minus x0, x minus x1, and x minus x3. Did you understand the law here? I think it's very easy to understand in this case. So, and now the denominator will be x2 minus x0, x2 minus x1, and x2 minus x3, beginning from x2, of course. And after replacing the corresponding values of this notice, we get here minus 1 over 2 in denominator. And the numerator will be just x plus 2, x plus 1, and x minus 1. So this is L2 of x. And now the last one, L3 of x. So L3 of x here, in numerator we have x minus x0, x minus x1, and x minus x2 without x3 now. And then the denominator is like this, x3 minus x0, x3 minus x1, and x3 minus x2. After replacing the corresponding values again, so we obtain 1 over 6 as coefficient here. And the numerator is without changing again, x plus 2, x plus 1, and x. So we obtain 4 corresponding L of x, Lix, from this polynomial. And then you can see if we replace, we said about it, yeah? So if you replace corresponding Li polynomials and the Yi here, respectively, so we get this kind of expression. just multiplying the first L0 to 3, L1 to 1 because of Y1 is 1, and the L3 to 2 because of, L2. L2 to 2 because of L2, Y2 is 2, and the last one, L3, this L3 to Y3. So Y3, this is here 0 just. So here written, remark, was it necessary to compute L3x? No, it's not necessary because of here you can see Y3 node is 0. That's why this is the not necessary for us to compute. When we multiplying, it will be 0 again. So now we got this polynomial P3. This is equivalent to the first polynomial. This one obtained with the first method, with the Vandermonde polynomials. So Vandermonde matrix. Here we get two equivalent representation of unique interpolating polynomial P3 of x. They are equivalent representations. You can see this one, the first one and second one, they are equivalent. Is it clear with these two methods? I want to hear your opinion.
Yeah, sure. It's clear.
Clear, yes. So now we have two methods and we can use any of them to find the interpolation of polynomial. So both of them are equivalent representations. And remark here, for every point x in which we want to evaluate the polynomial, means compute its value, we have to execute a number of algebraic operations of. First one, it is n squared over 2, equivalent to this operation, n squared over 2, or 4n squared. So we will consider this kind of operations now, algebraic operations. So here, this answer to this remark A. This answer called Ruffini-Horner algorithm. Let's suppose we want to evaluate the Pn of x polynomial written in the form. So Pn of x, this is the polynomial a plus a1x plus a2x, etc. And we have n additions here. an times x to the power n. So in this case, we have 1 multiplication. Here we have n multiplications. Because of here we have x n's power. Now this is equivalent to n squared over 2 operation. But we can rewrite this polynomial as in this form. Pn of x, it is a0 plus x. We can factor out x. You can see, if you factor out x, we have a1 plus a2, etc. plus an. Now, here, n minus 1 power. And similarly, analogically, we can continue this operation and again factor out x. So we get now a2 plus a3, etc. an x to the power n minus 2. If we continue this process, each time factor out x, we'll get here a0 plus x a1 plus x, then a2 plus x, etc. And the last one is an minus 1 plus an x. However, we have n's power polynomial in this case. Now, this one is equivalent to 2n operation. You can see here we don't have any powers. Is it clear? In this case, we have powers, and this is equivalent with n squared over 2 operation. But in this case, we have just one multiplication, not n multiplication here. Each time you can see one multiplication, etc. So now this is equivalent to 2n operation, algebraic operation. So, for example, from our previous polynomial P3x, which we got using wonder mode matrices, now we can write this polynomial as in this form also. So 2 plus factor out x, and again factor out x, and we obtain this expression. So it's also equivalent to 2n operation here, yes? We wrote this polynomial in this form. They are equal. And now, if it's clear, we'll move to the next section. So remark B now. We have the P3 polynomial, which interpolates 4 nodes from 0 till 3, yeah? So you can see here the graphs, and if we receive now the additional information, for example, now x4 and y4, so it was 4 nodes, but if we add the 5th node here, so it means we receive a new interpolation node with a corresponding value. Of course, what should we do? What should we do? Now we need to build and solve a new 5 to 5 system. Yes, from the first method, wonder mode method. Yeah, we need to build now new 5 to 5 because of now we have how many nodes? 5 nodes. It was 4 nodes, but now we build it will be 5 nodes, and we need to build 5 to 5 system and solve this system. Or if you work with the second method, we need to recompute this Li. Li in this case here, it's changed. So it was here 4 nodes, yes, but if we add here 5th one, it will be changed. L0, L1, L2, L3. All of them will be changed because of here we need to add now x0 minus x4, and here also x minus x4. Is it clear? So it's changed when we add here new nodes. It will be another example now.
Professor, I have a question.
Uh-huh.
So if we will have 0 in the denominator, what do we do?
If we have 0.
0 in the denominator, below, I mean.
It will be infinity if you have 0.
Okay, thank you.
So this one is clear. If you add 1 row, 1 node, it's changed, any of them. Because of here, it's depend on this nodes. Here we computed for 4 nodes, but when we add, it will be 5 nodes just. And it will be another one. So now, that's why here written recompute from scratch the Li and the P4. Now this is not P3 polynomial. No, it's P4 polynomial. Here you can see the graph of P3 polynomial with nodes 1, 2, 3, 4. Yeah, there was -2, -1, 0, and 1 from this table. -2, -1, 0, and 1. And the corresponding yi's was 3, 1, 2, 0. You can see here 3, 1, 2, and 0. These points, evaluation points, they are evaluation points, our nodes. But when we add the fifth node, it will be now a new graph, this graph now with violet. You can see this is a graph of P4. And but yeah, we have same evaluation points, same evaluation 4 points. So 1, 2, 3, 4, they are same. But the last one, 2, 5, this is not same. So we don't have here fifth one. Here we add fifth one, and the graph will be the another one. You can see from this table, from this graph. Is it clear? Students? Do you have any questions here?
No, it's clear.
Okay. Let's continue. And now we'll move to the next method, which is called Newton's method. Okay, so we have n+1 points of interpolation. So xi, yi, I from 0 to n, and n-1 degree Pn-1 polynomial, which interpolate the first n points. So you can see here we have n+1 points, and we have Pn-1 polynomial. So degree Pn-1, it is n-1. And in this case, we have n points, interpolations. So not n+1 n. We now write an n degree polynomial which interpolates all the n+1 points in this form. You can see we can write this Pn polynomial as sum of n-1 polynomial plus the last nth term, Qn of x. This is definition of Pn of x here. And the first step, Pn of x will have to interpolate the first n points in particular. So Qnx can be 0 in the xi, yi, or Qnx we can write in this form. Qnx we can write in this form. So we have two cases here. 0 or in this form, in generally, yes? So here Wn is already n degree polynomial, because of, you can see here beginning from x0, x0, x1, xn-1. If you multiply all of them, we get nth degree polynomial. N degree polynomial. So here an is a simple coefficient. This is a real number, an. This is the first coefficient, an. This is a real number. And now, what can we do here? We can define this an with this Pn and Pn-1. However, you can see if we replace this Qn with this form, if it is 0, it is clear. Pn of x equals to Pn-1. But if it's not 0, in generally, we can equating this to Qn of x. And you get here this 2 Qn of x. And you will get here this one, an, this expression, times an times Wn of x here. Instead of this one, you will get here an and W of Wn here. So now we can find An from this equation, yes? And An will be Pn minus 1. However, we will remove this Pn minus 1 to the left side and divide by Wn. Divide by this Wn. So you will get here this coefficient An. This coefficient An. So Pn of x must interpolate the points x and yn, and An will find with this equation by this formula. Now, so this coefficient, if we open this Wn, and when we open it, so we need to write this expression x minus x0, x minus x1, etc., x minus xn minus 1. Yes. So when we replace Wn with this expression, we get here function depending on how many variables? n plus 1 variables from beginning from 0 till n, x0 and xn. This is called Newton's ends divided difference. This is called Newton's ends divided difference. So now we will work with this difference now. Pn of xn minus Pn minus 1 xn over this expression, this denominator. So this is recursion formula, and we can work by recursion formula this. So firstly, let's begin with x0, y0. Notes x0, y0. So what we want to interpolate here and what we define here. So x0, y0, this is just p0 of x. Yes? Because of here, we have just first notice 0 and 0, x0, y0. It is just p0 of x. And it's equals to f of x0. F of x0 times this w0 of x. You can see here p0. Here we will put p0. Let me try to write here. So it will be p0 in this case. Yes. And this is what double w0. In the first case, in this case, x0, when x0, y0. And you need to multiply it to the right side of equation. Yes? So if we multiply it to the right side, we get this expression now. But in this case, w0 is equals to 1. Because we have x0 and y0. This is equals to 1. So that's why it's just fx0. fx0. Is it clear? Now, if we work with the second one, x1, y1, again, here we can see it should be fx0 plus this one times w1. Because of f1 now here it is just p0. Look here, p0 minus this, I mean p1 minus p0 over w1 times this equals to this one. But in this case, when we find this p1 of x, it will be fx0 plus fx0 x1 times w1. This is coefficient. You can see an we denoted with this one, fx0 xn. So this is just coefficient. From the previous slides also you can consider here just this is p0 now because of this one. P0 and W1 here. Is it clear? Now, similarly, we can find for x2, y2. Now, our P2, corresponding P2 polynomial will be fx0 plus fx0 x1 times w1x. This is equals to P1. Yes, look here from previous row. This is P1. And we need to add the third term here, this term. And this one gives us W2x. And so on. We can continue this process. So one more time. The main idea here is just finding this Pn with Pn minus 1 plus Qn. So with polynomial which is 1 minus 1 degree and nth degree. If Qn is 0, they are equal, Pn and Pn minus 1. If Qn gives in this form, we can define here using this Wn. However, this is the an here, just a real number. It is coefficient of this Qn. We can find an with Pn and W. And then after replacing Wn with this expression, corresponding expression, we get here this corresponding function f. So this is coefficient of our polynomial. And we will continue this process according to this algorithm. So here, fx0, this is just y0. This is corresponding node, y0. And fx0, x1, this equals to fx1 minus fx0 over x1 minus x0. So fx1, this is fx0, this is y0, here y1, here x1 minus x0. So you have your nodes xi and yi. Here we have nodes your xi, yi. And now using these nodes, you can find these coefficients also. We said this is a real number. Yeah, this is function of x0, x1, and xn, but they are constant. They are nodes. So this is constant function just. And similarly, you can find here x0, x1, and x2 by this formula. So you get here all coefficients of this polynomial. In this case, this is equal, P0 equals to y0, P1 equals to y0 plus this one, P2 equals to this y0 plus this expression, fx0, x1, this one, and plus this is times this one. Is it clear? Please, your questions. If you have any questions, you can give your questions. Students?
It's clear, Professor.
Clear, yes. Okay. So now, okay, if it's clear, we'll continue. However, this is online lecture and online lesson. I need to hear your reaction also. That's why I asked your questions. Okay, so let's continue. So this AN we call again AN called n's divided difference of Newton's n's divided difference. This AN. Okay, so now the interpolating polynomial. Look here, we said about it also Newton's form, right? Then in this form, so we said about it, and here the first coefficient is fx0. One more time. Okay, so next one, this one, etc., etc., and the last one will be fx0, x1, x2, and xn times x minus x0, x minus x1, and x minus etc., x minus xn minus 1. So this is representation of Pn with Newton's form. So we have Lagrange polynomial, fundamental Lagrange polynomial. Now we have Newton's form also. So here your f, the coefficient fx0, etc., xn, Newton's divided difference of order n here can be computed by the recursive formula. Can be computed by this recursive formula with the first condition, of course, fx0 equals to y0. So this is recursion formula, and this is Newton's form. So this is Newton's as order divided difference. Okay. Now remark, the order n divided difference is invariant with respect to any permutation of its argument. It means, so here we can see this order x0, xn. I mean, n's order here, divided difference, yeah? So Newton's divided difference. Now you can see here x3, x5, x2, and x7. So they are equal. So we can change order. We can do any permutations here. Invariant, it means it saved the value. Invariant. So this is permutation. You can change places, but the value will be the same as this one. Or you can see here the next permutation. Is it clear? So when we do any permutations, the value will be the same here. For order n Newton's divided difference. Okay. Now, divided difference of any order can be easily constructed by following the divided difference table. Given nodes and values to interpolate. So we have this table, divided difference table. You can see y0 implies x0 here. Then for x1, the corresponding one is y1, and the corresponding this Newton's divided difference, fx0, x1 here. So now x2, look here, like this, from the last one till the first one we can go also. So y here fx0, x1, x2 corresponds to fx1, x2, which is interpolate the y1 here and y2. So this is table, divided difference table. So our these forms we give with by this table now. So you can see here for x3 node, so it is implied to the fx1, x2, and x3, and then we'll find fx2, x3, then y3. So on the table, we read the interpolating polynomial coefficients f on the diagonal. The first one is just fx0, it's equals to y0. Then fx0, fx1, then this third one, x0, x1, x2, and then fourth one, x0, x1, x2, and x3. So here we can see there's this divided difference table, and finding these coefficients of interpolating polynomial. So again, important things are these coefficients we can find by this recursive formula, and the first condition fx0 equals to y0, xi, yi, they are nodes of and then after finding this coefficients, order and Newton divided difference, we can find Newton forms of polynomial, interpolating polynomial. We can find Newton's form of interpolating polynomial, and the order here is invariant. So if we change, it's invariant with respect to any permutation. If we change the order of these nodes, they are equal. And now, more in detail, the divided difference table is computed as. So now here we have just coefficients. Now, the value of these coefficients here. So in this case, you can see y0, it's just fx0. And here fx0, x1 equals to y1 minus y0 over x1 minus x0. And now we can find the third coefficient. It's equals to fx1, x2 minus x0, x1 over x2 minus x1. But we don't have x1 and x2. Yes, we have this one from previous one, but we don't have this one. So we need to find this one also. This is equals to y2 minus y1 over x2 minus x1. And similarly, we can find this here, the fourth coefficient. So fourth coefficient here is fx1, x2, x3 minus fx0, x1, and x2 over x3 minus x0. But we have this one from previous one. This is previous coefficient, x0, x1, x2. But we don't have this one yet. So we need to find this coefficient also here. And when we're finding this coefficient, it is equals to x2, x3 minus x1, x2 over x3 minus x1 from this recursion formula, of course. From this recursive formula. So from this recursive formula, we get these corresponding values of these coefficients. And now here we have fx1, x2, but we don't have now x2, x3. So now let's compute this fx2, x3. This is y2 minus y3 minus y2 over x3 minus x2. And we can continue this process and find other coefficients also using this given one. So if you know the first one, you can find others with this first one. This is recursive formula. That's why we need the first one here. Is it clear? Do you have any questions here, students? Can we continue? Okay. Now let's continue. So here again, our this given example, you can see we have notice, yeah, this table again, given table, xi is -2, -1, 0, and 1, yi 3, 1, 2, and 0. So now, so y0 is 3. That's why this is y0, the first one, yeah? It is 3. So we have corresponding notice. And now, when we find for x1 is -1. And you can see here from previous one, y1. So y1 here is 1. And now let's find this coefficient, corresponding coefficient to x1. So this is equals to, look here, y1 from this formula, y1 minus y0 over x1 minus x0. y1 minus y0, this is 3, x1 minus here x0. So we use just x0, x1, y0, and y1 for finding coefficient of x1, p1, I mean. Now, this is -2. And now, coefficient, this is a0, a1, a2 now. And now, we'll use here, notice, x0, x1, and x2, and y1, y0, y1, and y2 also. So after replacing here, you will get the corresponding value. So this is now fx1, x2 we need to find here. So if fx1, x2, we will find y2 minus y1 over x2 minus x1 here. And after replacing, we get 1. And now this is 1 minus previous one, 1 minus -2 here over 0 minus -2. However, this is x2 minus x0. And x2 minus x0 is this one, yeah, x2 minus x0, yeah, 0 minus -2. So it's equals to 3 over 2. And similarly, we can find we can continue this process and we can find the next one, coefficient of a3. So the coefficient a3 here is the last one. You can see we need to find this fx1, x2, x3, but we have this one. So this is equals to 3 over 2 from previous equation. And let's find this one. This one is equals to this one, to this expression. We don't know fx2, x3, but we know x1, x2. And let's find this x1, x2, x3 here. x2, x3. and this x2, x3 equals to -2 here. So you have all coefficients here, and you can find this x2 from this equation, and this x2, x3. This x2, x3 equals to -2, and when we replace it, so we get -3/2, and this -3/2 we'll put here. And after computing, we obtain -1. And now we have all coefficients here from this equation, from this form. Yeah, this is general form. We have all coefficients here. And now let's put these coefficients to our polynomial. And it will be, the first one is 3 plus -2 times x plus 2, because of here written x minus x0, and x0 is -2 minus -2, it gives us +2. And then 3/2, this is this third coefficient, yeah, third coefficient, x2, x plus 1, so it is x minus x0, x minus x1, so x minus x0 here, x plus 2, x minus x1, it is x plus 1 again. And the last one, -1 times the x minus x0, x minus x1, and x minus x2. So this is just x. So we get this form. You can see, let's compare with the previous answer. So you can see there is difference between Lagrange, fundamental Lagrange polynomial and the Vandermonde matrices. So it was this kind of polynomial. Here we have this kind of polynomial. And then with Newton's method, with Newton's form, we get this one polynomial. So they are equivalent, but not same. Yeah, they are equivalent polynomials. So the next time we'll continue from this place. We will add this new notice and compare what kind of differences will be between them. We'll continue the next time. So please, your questions now. Do you have any questions, students?
No questions, thank you.
Is it clear? Okay, so today we have practice also. It's beginning from 40, 40. This is 4 groups, ME3 and ME4. Okay, if you don't have any questions, we'll finish today's lecture and we'll continue on Friday. Thank you for attention.
Thank you also.
Mm-hmm.